Good evening and good morning, everyone. I am Salah Ramizi, visitor researcher from RIKEN AIP, and today I'm going to host the 15th TrustML Young Scientist Seminar. Before we invite our guest speaker, let me briefly introduce RIKEN AIP to our valuable guests and participants. So the full name of RIKEN AIP is RIKEN Center for Advanced Intelligence Project, and it was founded in 2016 as the research center for the next AIP project. So RIKEN is a very large organization, but AIP Center, in practice, it's focus and conduct Japan's leading AI research, which encompasses fundamental research technology, and it is headed by Professor Sugiyama. AIP aims to enhance AI research on real-world applications and encourages the collaboration with various researchers and engineers in related topics. We will be very glad to have you visit in our office in Honbashi in Tokyo in the future. And to our next speaker is Jenny. And now I will introduce our guests. So today's talk is about challenges in adversarial attack for motion estimation, and it will be presented by Jenny. Jenny Schmalfuss is a PhD student at the University of Stuttgart, and she's a fellow of the International Max Planck Research School for Intelligent Systems. Her research interests are at the intersection of computer vision and machine learning. So in her PhD, she investigated new ways to quantify and improve the robustness of motion estimation methods. Her goal is to enable robust motion estimation by understanding what influences the robustness of current models. So she will be presenting her recent work, and I will be stopping my screen. And Jenny, you're welcome to start. Thank you very much for joining us again.
So also a warm welcome from my side, and thank you again for the very kind introduction. So my talk today is about challenges in adversarial attacks for motion estimation. And to first give you an introduction into the topic, I want you to have a look at the picture that I put on my front slide, in which you see a train in snowy conditions. And this actually looks very much like what I saw today outside when I left my house, because here in Germany, we do have quite a lot of snow currently. And what I want you to do now is basically to picture yourself standing in a train station. And then you see a train that is approaching you. And now you imagine that it's snowing. And the amazing thing about our human understanding of motion is that you will see the train is approaching, no matter if it's snowing or if it's not snowing. If there is snow, you will not suddenly think that the train is driving away from you. And so this amazing robustness that we have in our human vision is unfortunately not something that we see in the algorithms that we are using to estimate motion from image sequences. And today I want to give you an understanding of how robust the methods that we're currently using actually are, and how that changes under different conditions. So let me start by introducing the optical flow problem. Optical flow is what I will call the motion estimation problem, where we start with a sequence of images, what you can see here. So we're basically starting with a video sequence, and then we take 2 frames out of it. And how we now represent motion is we basically look for the position of 1 pixel in the first frame, where it goes to the next frame. And this can be represented as 2D offset vectors. So you're just asking the questions like how much offset in X and Y direction will the pixel have from our first frame to the second frame. And this gives us, for each pixel in the first image, this will give us a 2D vector, which we can then represent in this colorful optic flow visualization here. And there, basically, each direction for the motion gives you a color, and the magnitude of the motion is then represented as color brightness. So this is the optical flow setup that we are talking about. And so there are a lot of methods to solve that problem. And of course, most of them nowadays are neural networks. In optical flow, when we talk about the robustness of optical flow, there is not so much work out there. And also there are not many adversarial attacks, because in optical flow, this is quite a new problem in a way. And so the first type of attack that we usually find in optical flow are adversarial patches. which I also show here. So there's a little patch embedded into this input image, and what we can see is that the flow that should be as it is represented on the top becomes actually something that is not representing the motion correctly anymore. The second class of perturbations that we do find in optical flow are global perturbations, such as L2 or L-infinity constraint perturbations, where we just add a certain amount of noise to our images and then also get a completely different flow than the ground truth. And the last class of attacks that we also have is what I call adversarial snow. So here we just add a bunch of particles into our scene, and then just through the presence of those particles, we can see that the optical flow that we get does not represent the motion in the images anymore, but actually vanishes in most of the parts. Okay, so we can see now that adversarial attacks do exist in optical flow, but there is not so much work out there. And now the question that I want to answer today is basically how robust are optical flow methods against LP attacks? And here I will focus on an L2 attack, which we presented at ACCB 2022. And with this kind of baseline knowledge, because the L2 attack that we have is currently one of the strongest attacks on optical flow, I want to continue to investigate how our methods fare when we attack them with non-LP attacks in the form of adversarial snow, because this gives us a more realistic estimate of how our methods could behave when they are employed in the wild. Okay. Now, before we can start to talk about LP or non-LP attacks, we first need to clarify a couple of things about optical flow and how we quantify robustness in those scenarios. So the first question is, how do we quantify robustness in optical flow? And as I said before, so we start with an initial flow field, which is just a bunch of 2D vectors. And so now, a typical definition for robustness is via the Lipschitz constant. So we ask the question, given that we can modify our input to a certain extent, how far does our output deviate in the worst case? And let's say that our output is our attacked flow f check. Then we can quantify our robustness as basically measuring the distance between this attacked flow f check and the initial flow. And in optical flow, how we typically compare flow fields is the average endpoint error. So for each pixel, you have a 2D vector, and then you compare, you take the L2 distance between the 2D vectors and average that over the whole image field. Okay, and then we can say once we constrain our perturbation to a certain size, we can then compare the adversarial robustness across different methods. Now, the interesting question is, of course, how do we get to this attacked flow that gives us then hopefully a good estimate to the robustness? And we do this via targeted attacks. So we prescribe some type of flow target. And here the flow target could be an arbitrary flow field. In this presentation, we will either see like this, this like random flow field, which has nothing to do with our initial flow, or we might also see a zero target, which is just white because the flow vectors are zero and therefore do not have any color representation. And now, in order to get a very good attacked flow, the goal for our adversarial attack is now to basically minimize the distance between this attacked flow and our target flow. And again, yeah, we measure this as the distance as the average endpoint error between the attacked flow and the target for certain limited size perturbations. Okay, and this is all the setup we need. So this gives you the definition for robustness and the definition for attack strength. And now we can continue to look at our LP constraint perturbation. And in this case, I'm going to introduce you to the perturbation constraint flow attack. So here, again, the idea is quite simple. We start with an initial input, which gives us an initial flow prediction from our methods. And now we want to add perturbations, which we constrain in an L2 sense, so that in the end, we do reach our target flow FT. And here the target flow is the zero flow, meaning no motion is predicted in the end. And what we want our attack to do is basically once we start to add some perturbations and we increase the magnitude of the perturbations, we can see that the perturbed flow slowly approaches our initial, the target flow that we had given. Now, in equations, the problem that we are going to solve is that we try to minimize some type of loss function between the target and the attacked flow by tuning our perturbations delta, while keeping delta in an L2 sense under some constraint. And the third and last thing is, once we add our perturbation to the image, we want the image still to be within a valid image range. So we want the colors to stay natural. And so now what you can see here are the two attacks that existed before our attack. So there was the patch attack, that was the first attack on optical flow, and an IFGSM type attack. And what we now wanted to do with our L2 constraint attack was basically to find a very strong attack that would give us a good robustness estimate. And so for this, we investigated different losses. So we have the average endpoint error, the mean squared error, and the cosine similarity. And out of those losses, we basically evaluated which gave us the strongest attack results. Then for the perturbation, we have a couple of choices to make, because we are working on image sequences of 2 images from which we want to predict the motion. So we can decide if we only want to attack the first frame or the second frame or both of them, and how we want to do this. And also there we tested different constellations and different things to see which gives us the strongest result. And last but not least, we also tested different ways to include the box constraint to have valid images after adding the perturbation into our optimization. And out of those, we then picked the strongest setup and tested a bunch of different methods. And just to give you a visual example of what our attack is capable of, I want to show you some examples here. So this is this basically the input sequence that we give to our method. So you can see that there is a car, and the car is driving down the road, and another car is coming towards us. And this is what you can see here in the flow representation when we do nothing to our sequence. And what we want to test now is basically, can our attack reach different targets? And the targets that we are putting is first the inverse flow target, where we just flip the direction of each flow vector. So we say each motion goes into the other direction now. And then we also do have the scintille target. And so most of the sequences that I'm showing you here do come from the Kitty dataset, which is kind of a benchmark in in driving. And so the target sequence that I put here is from the scintille dataset, which is a completely different dataset and has nothing to do with it. So just as a flow field that has no connection to the input data, basically. And what we can see is that the perturbation constraint flow attack is able to find very small perturbations, which you can see through that you hopefully can see nothing, because the images appear unchanged to us. But we can get actually very close to the inverse target flow. And the same also happens for the scintille target flow, where we can still get a very good approximation to the target that we have set. Then I want to show you some more illustrations. So hopefully you can see that, okay, it's not moving, so we jump over that. The next thing that I wanted to talk about is the perturbation types, because this is, I would say, a difference to classical adversarial attacks on classification, because here in our setup with the multiple input images, we also can make some choices about where to apply our perturbation to. And what we can do here is, since we have 2 input images, we can start by training disjoint perturbations, where we apply 1 perturbation per input images. So we then have basically 2 perturbations, 1 goes to the first frame, 1 goes to the second frame. But we could also decide to only train 1 perturbation that is then applied to both of the input frames. And this gives us the distinction between what I call the disjoint and the joint setting, where the difference is really how many perturbations do I apply to which input images. And here we only trained a single specific perturbation per frame pair. But we can, of course, also train universal perturbations where we then optimize either two or a single perturbation over a whole data set, so that it will then hopefully generalize better across new and unseen data. And what we found, and what I think is quite interesting, is that in the frame-specific case, things behave as you would expect. So you get very strong results when you go for the disjoint setting, because then you can, of course, optimize your perturbations so that they will give you a very strong attack. However, when we now go to the universal setting, we find that the strongest universal perturbations actually come from the joint perturbations. And here our ideas, or one explanation that we have found, is basically that optimizing two different perturbations for the two frames gives your optimizer too much freedom, and actually having only one perturbation that goes to both frames acts as a regularization and therefore gives us better results in the end. And as like small visual example of what this might look like, we do have the frame-specific perturbations in the two top rows and the universal perturbations in the bottom row for one specific network. And we can see here for the zero flow target, where our target is all white, we can see that the disjoint perturbations actually give us most white in the target and the frames, while the universal perturbations do have a relatively minor effect on the images. Okay, now after the technical details, we took our strongest attack setup and evaluated the whole set of methods for optical flow methods that is commonly used by their quality and robustness jointly. And for the quality, we take some error measure from the Kitty dataset, which is a benchmark that is very commonly used in optical flow. And then we took our strongest adversarial attack setup and measured the adversarial robustness, so the distance between the initial flow and the attacked flow, which means small values mean we do have a good robustness. And our ideal method that has an amazing quality and an amazing robustness would be down here. And when we now take a set of representative optical flow methods, we actually find something very interesting. We find that there are different groups that behave differently. And we start with SpyNet. SpyNet is a relatively old method, which has kind of a bad quality, but a very good robustness. When we now continue with FlowNet2 and PWCNet, we find that those have kind of a medium robustness and well, much better, but still mediocre quality. And when we now move to methods that are leading on the quality benchmarks like RAFT and GMA, we find that those actually do have the worst robustness with regard to our L2 attack. And this is, I would say, like quite interesting in that regard, that in optical flow people usually only look at the quality benchmarks, but they never really consider the robustness as a value that they would report in their papers. And when you now only look at the quality benchmarks, then you're also buying in a very bad adversarial robustness. And so these findings are what came out of our L2 attack, but then we continued to ask the question, okay, so this holds for these artificial L2 type perturbations. So what does happen when we progress to a more realistic scenario? And this is how we came up with the idea of our adversarial snow, where we said, okay, we considered these L2 perturbation, there seems to be this very clear trend, this very clear trade-off between quality and robustness, but is this really all? Or is there more to it? And what we do consider now is a more realistic attack, where we model snow as a particle effect, and we do so explicitly. So the question is, why don't I just use some standard snow augmentation, and also there have been adversarial attacks with snow and weather phenomena. Why can't I just use one of them? Why do I need to do something special for optical flow here? And I hope that you can basically see how these two frames on the left are switching, so you can get an impression of how the motion should look like in those frames. And the challenge for optical flow, since we're doing motion estimation, is motion is really important, and also like 3D scene geometry is really important, because what we want is a snowflake that is embedded into our 3D scene. Even if it would not be moving, we want that it kind of changes, it organically integrates into your scene. Let's say when your camera switches from a first position in the first frame to a second position. So in pixel coordinates, that wouldn't be the same. So that there should be a change. And also we want our snowflakes to have a consistent motion over time in the 3D scene. So we want our snowflake to start somewhere in the 3D space and then fall along a certain vector and then be somewhere else in the 3D space and then render that to the camera. And this is something that has that I haven't seen in the literature so far. And this is why we decided to perform this adversarial snow attack on optical flow, given all these constraints that we need for motion estimation. And so this is basically how we did it. So I told you before, so there are two challenges. The first one is that we need to get our 3D motion into the scene, which means we need to get into the 3D space. And also we need to have our motion over time. And the second thing is we want to have a realistic appearance. So we want our snowflakes to look convincing. And in order to tackle the first one, 3D motion, we started with the very simplistic parametrization of our snowflakes. So we start with an initial position in the 3D space. And then we say, all right, now we allow a certain offset for our snowflakes that can later on be optimized. And the position that comes out after this offset is what we see as starting position for our snowflake, which is then rendered into the first frame. And then our snowflake falls along a certain vector that we prescribe. So we would say that every snowflake falls down to a certain extent. And when it hits this like preliminary landing position, we also allow a second offset that can later on be optimized. And adding this offset would then give us our final landing position, which is rendered into the second frame. So this is what we basically did on the modeling side. And then we took a couple of measures in order to get those snowflakes to look realistic. And so here the concept is basically we find the points in the images that correspond to the snowflakes. And once we have those points, we then apply a flake template, which we pre-created. And we start by a set of snowflake templates that are not perfectly circular, but have like a variety of shapes, which we initialize to the positions. Then as a next step, in the second step, we scale those flake templates. And we scale them according to their depth, so that snowflakes closer to the camera appear closer and snowflakes further down, further in the back, are smaller. Then we do something very similar with the transparency. So we also make snowflakes in the back more transparent. And last but not least, for the snowflakes that are very close to the camera, we add some out of focus blur. And we also handle occlusions, because in the dataset on which we performed those experiments, we do have depth maps. So we can check for each snowflake if it would be visible in the frame, and then we don't render it in case it isn't visible. And now all these measures give us our realistic looking and also realistically behaving snow. And to get from this initial, from the snow initialization to something that we can now optimize, we of course have to define a loss function. And the loss function that we have been using here again minimizes the average endpoint error between some prescribed target flow and the attacked flow. And the second thing that we added is a term that basically manages the offsets that we allow across around the starting position and around the landing position. And so we sum over the length of all these offset vectors. But the second thing that we do is we also scale them by their depth, or more precisely, the inverse of their depth. And here the idea is that we want to allow larger offsets for snowflakes that are further in the back and smaller offsets for snowflakes that are closer to the camera. Why is that? Well, if you would allow offsets that have the same size for both of these positions, then what you would get is basically for snowflakes close to the camera, when you make a large step, suddenly your snowflake is out of the camera. Whereas when you are further in the back, you can still allow larger offsets while still keeping your snowflake in the field of view of your camera. And yeah, this gives us now the tool to convert our random snow initialization, or which would just be a snow augmentation, into optimized adversarial snow. Okay, let's have a look at what this can do. So here again, there are two sequences, and you can see the original flow that is predicted by a high quality network. Now, when we add our random snow to the scene, what you can see is that there are some artifacts, also because the snow by construction has a certain motion to it. But all in all, the scene still looks quite convincing. And now if we start to optimize our snow towards the 0 target, we can see that a lot of the motion that is detected in the scene suddenly vanishes, even though you can still clearly see what's going on. A second thing that I would like to mention here is these snowflakes are only in very specific parts of the scene. So you can still see a lot, and there is still a lot going on, and there are still a lot of places in those scenes where we don't have any snowflakes. Now I want to show you two experiments that we did. And so the first experiments that we did was we wanted to find out if our snowflakes behave as one would expect, meaning if we increase the number of snowflakes to optimize, do we get a more powerful attack? And so what you can see here is the attack strength. So small values indicate a very strong attack, and you can see that the number of snowflakes goes up from 1,000 to 5,000. Below, you can also see some visualizations for you to have an impression of like what snow density 1,000 snowflakes and 5,000 snowflakes in a scene would mean. And here we do have 3 optical flow networks. And those networks were not chosen at random. They were chosen to represent one of the groups that I pointed out to you earlier in the context of the L2 attacks, where SpyNet is our network, which had an amazing robustness, but a very bad quality. FlowNet 2 had medium quality and medium robustness, and GMA had an amazing quality, but a bad robustness. And you can see for all of them, as we increase the number of snowflakes, our attack strength goes up. So this is what we would expect. And now that we know our attack behaves as expected, we can have a look at some more interesting things. We can have a look at the optimization parameters and what their influence on the attack strength is. Here again, we have SpyNet, FlowNet 2, and GMA. So bad robustness, medium robustness, good robustness, bad, medium robustness, and bad robustness. And we start by comparing the values to what happens when we just throw in initial random snow into the scene. And we can see even there, this does already have some attack strength, and this acts as our baseline before we start to optimize certain parameters. And the parameters that we optimize are the offset to the starting position, delta t, the offset to the landing position, delta t plus 1, and the transparency theta, which we take as an approximation to color information. And we can see that the best attack strength, so the smallest values, are achieved once we start to optimize the positions. There are some differences between the starting and the landing position, but Like for now, we can just say when we optimize positions, then we get a stronger attack. Whereas when we optimize the transparency, we do see a little effect, but we do not get much over the performance of random snow. And that is nice, because now we see that our motion algorithms actually look at the motion that's going on in the scene. And also, in order to confuse them, we actually have to change something about the motion of our snowflakes. So it's not enough to just tune the color in a way. And then we also see that when we optimize all three of those parameters, we do get the strongest attack. But what's very interesting is something that you will notice when you compare the numbers of the initial snow to our best attack. Because currently we were just discussing attack strength. And now if we compare those two values and subtract them, we do get an estimate to the adversarial robustness of our methods. And you can see that this value is actually smallest for GMA. And that comes to a surprise, because a small adversarial robustness means our method is great in terms of robustness, which wasn't the case for GMA when we attacked it with our L2 attack. Their GMA was extremely unstable, and now with regard to the snow, it's suddenly the most stable method that we tested. And one idea that, or one thing that could explain it is when you have a look at the results for GMA on the left and the less well-performing FlowNet 2 on the right. And what I want you to notice about the GMA results is when you have a look at these colorful flow predictions here, you can see that GMA is able to pick up single snowflakes in the frame. So it actually detects single snowflakes and is therefore potentially able to differentiate between a snowflake that is inducing some wrong motion and the background where it still can predict the motion correctly. Whereas when you have a look at the results for FlowNet 2 is not able to pick up single snowflakes. So the overall wrong impression that comes from the snowflakes is then propagated onto the whole image, and therefore could explain why GMA has better results in terms of snowflake robustness. Because here, the quality that GMA has is helping to figure out where the snowflakes are and then kind of contain the effect of the snowflakes to only a small area. Okay, so what have we seen today, or what did I hopefully show you? So we have seen that optical flow methods are indeed vulnerable to both LP and non-LP attacks, and so in that sense they are not an exception, as most neural networks. But we have also seen that when we attack them with an L2 attack, we can see this very clear trend that quality and robustness seem to be two very contradicting goals. However, when we now move on to non-LP attacks and to this case of adversarial snow, we have seen that quality can actually help because it can help you to figure out where single snowflakes are. And so in that sense, there is no easy answer to the question, how robust are optical flow methods? As always, it depends, but this gives us some very nice points to start with. And also it is kind of a nice result in that sense that now if you go to the quality benchmarks and take one of the highest quality methods, you can still get some robustness against certain types of attacks. And last but not least, I want to briefly show you with whom I did this work. So the perturbation constrained adversarial attack, which we published at ECCV, was worked together with Philipp Scholze and Andres Brun. And the adversarial snow project was something that I did together with Lukas Mehl and Andres Brun. And yeah, with this, I'd like to thank you for being here and for staying with me. And if you have any questions, then I'm really happy to answer them.
Thank you very much, Jenny. It was very insightful. I have myself some questions, but I received also two questions query them to you. First one, did you evaluate approaches to robustify models like adversarial training? And I don't know.
Should I answer directly?
Yeah, please.
So we haven't been looking into that so far because right now we've basically laying the basics for that by developing these adversarial attacks. But also having a look at these adversarial training is something that I definitely want to do next. And so unfortunately, I don't have any numbers on that yet.
Okay, thank you. And another question is for slide 13, what is the cost of the snow generation process? I'm not sure to understand.
This one here. Okay, so I have to say the setup is very expensive because how it's currently done is that we're pre-generating the initial positions and the initial snowflake templates, and this really takes a while because you have to sample like from the depth and then find snowflake positions that are valid in your frame, and then they do all the scaling. But the nice thing is you only have to do this once per frame. So or even if you would do it across a certain set of frames, you would only have to do it once in the beginning of your training. And then the optimization and basically taking those frame templates and the 3D positions and then rendering that to the frame is not that expensive anymore, because from there on, it's basically projecting your 3D your 3D positions onto the 2D space, doing some interpolations, but that's not something super costly. And of course, it depends on the number of snowflakes. So the more snowflakes you need to add to your image and to your image plane, the more expensive also your optimization becomes. But maybe to give you an idea on to generate 1,000 snowflakes on 8 CPUs takes about half a minute, but then in order to train it, we do get, we can do a couple of iterations in a few seconds on a CPU when we train it. When we train it.
I see. I guess that it answers the question. Thank you. Anyone else? You can either say it or put it in the chat. Otherwise, I have myself some questions, more high-level questions. I was thinking, we have a question from Johan. Please go on. Yes.
Yes, sorry, I have a technical issue. I understand well. You during the test you train only on the CPU, or
sorry. No, it was like if we train on GPUs, but the measurements I can only give you for CPUs because that's sometimes what I do when I experiment around. For a full training on a couple of sequences, we trained on one A100 and it was about 2 hours for the full data set, so it's not that long actually.
Okay, understand. And the amount of memory, it's I don't know, it's important, or it's changed during the training?
Yeah, it heavily depends on the amount of snowflakes that you put. Okay. I would say like up to 5,000 snowflakes, it's still feasible on a single GPU, but after that, the memory is what limits you.
Oh, okay. Interesting. Thank you.
Thank you very much for the question. Anyone else? I had a question about the threat model, because here it's about security as well. I was wondering, your approach still requires access to the model, to some information about the model, the gradients. Do you think that we can find a way to extend it into a black box setting, or at least a gray box setting? And if it's feasible in this case, using just the logits, the output, the final outputs?
That's a good question. So I haven't looked too much into that, but my feeling would be that for the adversarial snow, it might be a bit complicated. Also because for the adversarial snow, we have seen that it does not transfer well across models so far. And so, yeah, my feeling would be that currently it's complicated, but I think if you would have some ideas about how we could do this, that would also be something that I'd be interested into looking at.
Okay, thanks. I will discuss it with you later on, but I have, sure. Anyone else? It can be technical questions or more general questions. In that case, I can conclude with one general question about the next steps and the perspective that you see for this kind of problems, and what are the challenges that you think are the most important to solve in this case.
Okay, so the things that we're like, the outlook for this project is basically that we're currently investigating more effects. So not only snow, but also something that has like more color, which also includes effects like rain and all of that. So there, the challenges are mostly like how to model it and how to get it in a nice way and differentiably onto your image. On a broader perspective, this work on adversarial attacks for motion estimation is kind of the basis for all work that can later on build on making optical flow in general more robust towards adversarial attacks. And I think one of the building stones for that, of course, is then to look into adversarial training to some extent, but we've also been running some experiments on more robust architectures, which also show promising results. So I think in general, now with these adversarial attacks, we have tools to quantify the robustness of optical flow methods. And now the next steps are building on that and making optical flow more robust by using the tools that have been developed for classification and seeing how they work for optical flow, but also looking into the architectures of the networks themselves and see if you could do something about the architectures and get more robustness from there.
Okay, great. Thank you very much. Any final words, or we can close the session? Okay, so thank you everyone for joining today, and thank you again, Jenny, for being our guest. It was a pleasure and a very insightful talk, and I'm looking forward to our discussions later on. So for Jenny, on the website, you have access to the email of Jenny, but also some information about her. And once the video is ready, you will find more. We'll find the link also on the website. Also, we keep promoting it on Twitter, so just follow us, and see you everyone for next week. Next Monday is our talk also about adversarial attacks and security. So next Monday in the morning. Thank you everyone, and looking forward to seeing you for our next sessions.